In this video, I want to prove the derivative with respect to x of the natural log of some function of x. So to do this, we'll start with just the derivative of the natural log of x. I'm going to show that's equal to 1 over x. So to do this, I'll just go through our definition of the derivative, which is the limit as delta x approaches 0 of f of x plus delta x. Well, in this case, our function's natural log of x. So f of x plus delta x will be natural log of x plus delta x minus f of x, which is just natural log of x, over delta x. So this is our derivative of the natural log of x if we can evaluate the limit. And in our other examples, when we use this limit definition with just an algebraic expression, a polynomial or something, we could go through simplification to find it. When we did our trig functions, we used trig identities. When now doing it with natural logs, we'll use our log properties. So the first thing I want to do is combine the two logs into one. So it will become the limit as delta x approaches 0 of the natural log of x plus delta x over x. Just using our log property that when you have a difference of two logs, it becomes a quotient in the argument, and that's still divided by delta x. Then we can do more from there, because the divided by delta x is the same thing as being multiplied by 1 over it. So we can simplify to the limit as delta x approaches 0 of 1 over delta x multiplied by the natural log, and on the argument of the natural log I simply split the fraction. It will become 1 plus delta x over x. So now from there, what can we do? Well, I can use another log property and just pull that power or the multiple in front to make it the power on the argument. And this is really going in reverse to what you're used to doing, but just reversing that log property, I'll get the limit as delta x approaches 0 of the natural log of 1 plus delta x over x raised to the 1 over delta x power. So now we're starting to get somewhere, and I'll make a substitution now that will make this work. I'll make the substitution that n is equal to x over delta x. So you ask, well, what is that going to do? When we rewrite it, it's the limit, but now it's not delta x, our variable's n. But if we think about it, as delta x approaches 0 here, what is going to occur? Well, as delta x is approaching 0, x is divided by 0. Well, dividing by 0 is infinity. So this will be the limit as n approaches infinity of the natural log of 1 plus, well, delta x over x is just the reciprocal, so that'll be 1 over n. Then we'll have a power of 1 over delta x. Well, we can write that as n times 1 over x, because if n is x over delta x, n times 1 over x is x over delta x times 1 over x. The x's cancel and we get our 1 over delta x. So now from there, let's use a log property again, and we can pull our 1 over x out in front. So it becomes the limit as n approaches infinity of 1 over x times the natural log of 1 plus 1 over n to the n. And maybe you're starting to see it here, but let's make one more move to make this a little clearer. Our limit's in terms of n, so 1 over x is really a constant in this. So let's say that that is 1 over x times the natural log of the limit as n approaches infinity of 1 plus 1 over n to the n. And this is just using our limit property. Since x is a constant, our limit's in terms of n, we're just focusing on the inside of the argument of the natural log now. Well, whether you may have seen this before, you may not be familiar with it, but the limit as n approaches infinity of 1 plus 1 over n raised to the n, that's our definition of e. the natural number. So this will be equal to 1 over x times the natural log of e. But the natural log of e is simply 1 because natural log is base e. So the natural log of e is saying what number do you have to raise e to get e. It's simply 1. So that'll simply be 1 over x. So we've shown in that the derivative with respect to x of the natural log of x equals 1 over x. Well, what do we do if it's the natural log of some function of x? We can just use the chain rule then. So if we have the natural log of some function of x, let's just use our chain rule and say that our outer function g of x will be natural log of x, and our inner function h of x will equal the inside f of x. So that f of, or g of h of x would be equal to the natural log of h of x, which is f of x. So we just took our natural log of f of x and wrote it as a composite function, g of h of x. So with that in mind, knowing our chain rule, our derivative will be g prime of h of x times h prime of x. Well, what is g prime of h of x? Well, g prime of x is the derivative of the natural log of x, which we know is 1 over x. So g prime of h of x is going to be 1 over h of x, which is f of x, the argument of the original natural log. Well, that's multiplied by h prime of x. Well, if we take the derivative of h of x, it equals the derivative of f of x, f prime of x. So when we simplify, we can show that the derivative with respect to x of the natural log of some function f of x will be equal to f prime of x over f of x. So that's simply the derivative of a natural log is the derivative of the argument divided by the argument. So let me give a concrete example to make that a little clearer. If we have the derivative with respect to x of the natural log of x squared minus 4x plus 3, that derivative is equal to the derivative of x squared minus 4x plus 3 divided by x squared minus 4x plus 3. And we can just use our basic power rule and sum and difference rules. For the derivative of that polynomial, it'll just be 2x minus 4 divided by x squared minus 4x plus 3. So we've shown in this that the derivative of the natural log is just the derivative of the argument, the inside part, divided by itself.